Okay, hi everyone. Welcome to today's Q-Farm seminar. I'm very excited to introduce today's speaker, Liang Jiang. So Liang got his bachelor's degree from Caltech and did his PhD at Harvard with Michel Lukin, graduating in 2009. And he made some pretty important contributions there to understanding how quantum repeaters can be used, and then also experimental work. He went on to Caltech again as a postdoctoral fellow working on theory. And in 2012, he joined Yale. So very recently, he has moved to University of Chicago to the Pritzker School of Molecular Engineering, and he's won numerous awards that I won't go into, like Sloan and Packard. And today, Liang will talk about robust quantum information processing with bosonic modes. Before he starts, I just want to also say that if you can put your questions in the chat room at the end of the talk, or maybe at some point in the middle, we can I'll try to pose them to Liang. So thank you. Thanks, Liang.
Okay. Hi everyone, and well, it's a pleasure to have the opportunity to actually give this virtual seminar. And you probably see the background of this the bridge in San Francisco. But but today I'll talk about this robust quantum information processing with bosonic modes. So it's kind of a combination of theory and experiment demonstrations. And so maybe as a, let me see how to get this to work. Yeah. Okay. So maybe as a motivation that we know that actually bosonic systems has applications for various quantum information processing tasks, including computation, communication, metrology, and the quantum simulations. And for example, you can use superconducting cavity to process information, and all the fiber modes that you use for communications are bosonic modes. And the LIGO gravitational wave detectors, cavity resonators, and these boson samplings is actually using bosons. But for these bosonic systems, actually one major challenge is actually the excitation loss. So while you store information in the bosonic modes, but typically after a cavity lifetime, the excitation will be lost. So is it possible to store information longer than the characteristic lifetime of the cavity? And that's actually some question we'd like to explore theoretically. And if possible, can we demonstrate we can store information longer than the characteristic time of a bosonic mode? So maybe before we proceed, there's actually some a no-go theorem saying if you just have beam splitters or squeezers, and all those are called the Gaussian operations, and which can be implemented with the quadratic Hamiltonian. For those operations, actually, there is a no-go theorem say that you will not be able to protect against these excitation loss errors deterministically. So therefore, we need some additional control knobs in order to consider even tackling this problem of correcting excitation loss error. So that's why maybe let's start with this quantum control of bosonic modes, because what we want is not just the beam splitters and squeezing operations. We want something more powerful, which essentially we need universal control of the bosonic modes. And or put another way is we need some nonlinearity to control the bosonic modes so that we can do something beyond what we can do with the beam splitters and the squeezers. So, to be specific, in this talk, I'll be mostly focusing on the microwave modes, which you can control it using the superconducting devices. So for example, in the figure on the upper left, you see that there is a superconducting cavity, which made of aluminum. It's a 3D cavity, and when you cool it down below the superconducting transition temperature, then the whole cavity will be superconducting. And here you see there are two trenches which correspond to two cavity modes. And there's a semi-transparent chip, which is a sapphire chip hosting a Josephson device, which is a transmon qubit. So you can think that you have a transmon qubit, which coupled to these different cavity modes, and one will be a storage cavity that stores information, and the other cavity will be the readout cavity that allow you to read out the state of the transmon qubit. And for the purpose of this discussion, we're mostly focusing on the storage cavity and the transmon qubit. And when the cavity resonant frequency and the transmon qubits, they're largely detuned, and typically they can be each be like a few gigahertz, and if they're detuned by about a gigahertz, then there is essentially no excitation exchange between these two modes. So the process only happens virtually, and if you do the second order perturbation, then you can derive an effective Hamiltonian, which has a cavity term, qubit term, and a dispersive coupling between the cavity and the qubit. So these individual modes will have resonant frequencies of order gigahertz, while the dispersive coupling can be of order megahertz, which is actually much larger than the decoherence rate of the cavity and the qubits, which is of order kilohertz. So essentially, you can treat this as like a closed quantum system with just dispersive coupling between the cavity and the qubits. And one thing I should point out is that the Josephson effect is actually a nonlinear effect, which enables us to have the qubit, which is also a highly nonlinear device. And as later in the talk, I will show like how we use this nonlinearity to enable us to achieve a universal control of the cavity or the joint cavity qubit system. But maybe another thing that we want to point out is actually that in the past few years, there have been significant developments in these superconducting devices. For example, the superconducting cavity, once it goes to the three-dimensional cavity, as shown here, the lifetime can be of order milliseconds or longer, which can be hundreds of times longer than the typical qubit coherence time. So that motivates probably we can store information in a cavity to have a better storage device. And moreover, that we can also perform the quantum non-demolition single-shot readout of a qubit, which is this transmon device. And you can do the readout with like 300 nanoseconds with fidelity better than 99%. And this has been demonstrated in multiple groups like in the past few years. And moreover, with the real-time adaptive control, you can perform like which will be needed if you want to like perform a gates conditioned on the previous measurement outcome. So that is crucial also for quantum error correction, as we will discuss later. So maybe now let's actually look into this, like how we actually control such a cavity qubit hybrid system. So here, actually I put this dispersive term in front of the qubit. You can think it as that it depends on number of photons in the cavity, there will be a different resonant frequency of the qubit. And the shift of the frequency for the qubit is proportional to the photon number. And the control knobs we basically have two control knobs. One is you can drive the cavity, okay, shows in the term here. Basically, you can displace the cavity. The other knob is you can drive the qubit with different frequency tones. And here I write it as a sum of different frequency tones associated with the different numbers you have in the cavity. So that assume the drive strength is weak compared to the dispersive coupling, then you can selectively drive the qubit conditioned on the state of the cavity. So to make it clear, let's tentatively forget about this, like go to the rotating frame of the cavity and not driving the cavity. So this will be the energy levels associated with the rotating frame in the cavity. So there are different numbers associated with the cavity state, different excitation numbers in the cavity, and also the lower manifold associated with the qubit in the ground state, while the upper manifold associated with the transmon qubit in the excited states. And with more cavity photon numbers, because of dispersive coupling, the energy difference between ground and excited states are shifted by integer multiple of chi's. So now suppose you drive one frequency tone, which is omega qubit minus 2 chi, then essentially you only drive the qubit when there are 2 photons in the cavity. And that allows you to do, like, for example, you can do a 2 pi rotations and transfer the population back to the n equal to 2 ground states. But there will be a non-trivial phase associated with this particular photon number, because what you're doing is essentially like you, for this particular 2 level with 2 excitation qubit in the ground or excited states, then you will have a 2-level system and you're carving out a non-trivial area in the Bloch sphere. And that area will induce a geometric phase that's imprinted to this particular photon number. And that is this geometric phase gate that you can, the phase you can fully control by tuning the phase difference between the 2 pi pulses, which is showing here, so that you can impart arbitrary phase to this particular photon number. And these drives, you can apply it simultaneously for different photon numbers. And for each photon number, they will have its own two-dimensional subspace, and you can carve out a certain area in the Bloch sphere to impart a phase. So overall, what happened is that you perform an operation which imprints a geometric phase for different photon number at your control. And essentially, you have a unitary operation, which we call the selective, number-dependent, arbitrary phase gate, the snap gate. So for different photon number, you can have a different phase. So if the phase is proportional to photon number, you imprint, essentially the evolution is similar to a frequency detuning. If the phase is proportional to photon number square, you perform an operation which is like a Kerr effect. And if the phase is proportional to photon number cube or higher order, then it's a higher order Kerr effect. So basically, by borrowing the nonlinearity from this two-level system, we can implement arbitrary order Kerr effect to our bosonic system. And this operation is highly nonlinear, but by itself, it's not universal because the photon number is conserved. So we need another operation to change the photon number. And that operation is actually pretty simple. You can perform a displacement operation of the cavity, which will change the photon number. And so combined with the snap gate and displacement operation, and you can see like you can connect, all these levels can be connected. So that's kind of a necessary condition for universal control. And we can show theoretically a detail in this paper that indeed you can perform a universal control over not only the qubit and not only the cavity system, but actually even the joint qubit cavity system. You can achieve universal control. So just let's take a look at some simple examples. So this first example is we can prepare a single photon on demand. So suppose we start from a vacuum state. We can perform a displacement operation over the cavity. And this is the coherent state we prepare. And the upper panel corresponds to the different population distribution with the phase indicated by the arrow, by these arrows. And the lower panel corresponds to a spectral measurement of the resonant frequencies of the qubit. You can see that these different peaks correspond to different photon number distributions for the cavity. And now you perform a snap gate by shifting the phase associated with the 0 photon by pi. And basically rotate the phase by pi for 0 photon. And this is the Wigner function that we measured in real time from the device. And the photon number distribution doesn't change as verified by the qubit spectroscopy. And then you can perform another displacement, shift this state back to the origin. And that allows you to prepare a single photon state with a negative Wigner function as shown here. And in terms of photon number distribution, you can think it as the displacement allows you to interfere with different photon numbers. And by arranging the coefficient appropriately for specific choice of alpha, essentially 99% of the photon gets refocused back to single photon Fock states. So by this simple 3-step procedure, you can deterministically prepare a single photon state with a fidelity higher than 99%. And if you want to higher fidelities, you can do more iterations, which you can get essentially arbitrary high fidelity in theory. And the practice is limited by the photon loss while you're preparing these operations and also the decoherence of the transmon, as we'll discuss later. So this is preparing a state. We can also perform arbitrary unitaries. For example, you can perform a unitary operation which shift the photon number by 4 and modulo 8. This is kind of the unitary. And instead of like doing the snap operation, we actually can relax the requirement. Like we can perform the qubit drive and the cavity drive simultaneously. And then the evolution becomes complicated. So instead of doing all the computation like by hand, we let the computer to find the optimum pulses using the grip algorithm. And here is the qubit drive and the cavity drive with the real and the frequency, real and imaginary frequency shown in red and blue. The pulse took about 1 microsecond, which is determined by the dispersive coupling strength, which is of order megahertz. So by this pulse, if you start from the vacuum, you can prepare a single photon Fock state, 4 photon Fock states. And based on counting of the rings, you can verify that this is indeed a 4 photon Fock state. And the fidelity is of order 90% or a little bit higher. And instead of doing a tomography for this particular gate, which has a 8-dimensional Hilbert space, we'll just do a tomography for another particular choice of the coding called the cat code. And you can verify, like using randomized benchmarking, the fidelity can be about 99%. So this is kind of something that which I'll come back a little bit later, talking about the different encoding for the bosonic system. But at least we can show that you can do arbitrary unitaries to a particular choice of the subspace. But actually, unitary operation is not the most general allowed by quantum mechanics, because more generally, we can even consider doing something called the complete positive trace preserving map, CPTP map. Because instead of consider a deterministic, like a unitary operation that preserve the purity of a quantum state, maybe there are some decoherences going on, so that the evolution may not be unitary, and it's represented by this map, which is, you can also represent the CPTP map in the cross representation. So you can think that someone is throwing a dice, which determines which trajectory the system is evolving. So, and each of the trajectory is labeled by I, and for each trajectory, there is a cross operator Ki acting on the system. And there, for this case, we have n such trajectories. And generally, the n will be no larger than the dimension square, where dimension is the system dimension. And for the special case where n equal to 1, the CPTP map corresponds to the unitary evolution, where Ki corresponds to the unitary. But generally, you can have multiple paths to choose. And generally, for CPTP map, if you want to implement it, if you look at Niels and Tron, they have a recipe that you need a D square level ancilla to co-evolve with your system, and you trace away the ancilla, you get the desired evolution. But this operation is actually very resource consuming. Suppose you have a 10 level qubit, you need actually 100 level ancilla to do this operation. So one question raises is that, can we actually perform the CPTP map more efficiently? Instead of using D square level ancilla, we want to minimize the use of the ancilla, or the dimension of the ancilla. And it turns out that it's possible, but we need an additional requirement that we need to be able to repeatedly use ancilla. And if we allow this repetition or repeated use of ancilla, then we can actually perform a CPTP map with actually the minimum level ancilla, which is 2-level ancilla. And here is actually the idea. So it turns out we can repeatedly use a 2-level ancilla to achieve to implement CPTP map. So suppose we have a D-level system, we have a 2-level ancilla. We can think the ancilla as a transmount D-level system as our qubit, or our cavity. And we can couple the ancilla and the D-level system together and perform a measurement of the ancilla, and we get 1 classical bit of information. And we pass that 1 classical bit of information forward and use that to control the second round of the operation between the system and ancilla. And then we measure the ancilla again, and then we get 2 classical bits of information from the first 2 rounds. And then we use that to control the unitary for the 3rd round, and then get a 3rd classical bit of measurement outcome, and then use it to control for the 4th round, and so on. So it turns out that overall, we need this log 2n, where n is the number of paths that you have for this cross map. And it's bounded by 2 times log 2d, which scale logarithmically with the dimension of the qubits. Then you can actually achieve the desired evolution by simply forgetting about the measurement outcome from the intermediate steps. So that gives you an efficient way to implement the CPTP map, with the depth of the circuit only scales logarithmically. And one can show this is actually the optimum way to design such a circuit. And moreover, experimentally, we actually have all the ingredients needed to implement such a CPTP map, because the coupling between the qubit and ancilla, if the qubit we treat it as a sequence cavity, and the ancilla is a transmount 2-level system, then we can couple these qubit and ancilla with arbitrary unitary control, as mentioned in the early on. And also, we know that we can do single shots quantum non-demolition measurement of the ancilla. And with real-time FPGA adaptive control, we can use the measurement outcome to determine the later operations. So therefore, all the elements that needed for this procedure has already been available. So we can just use it for our experiment. And just as maybe a recap, that this is actually the most general map allowed by quantum mechanics. And it implements any physical processes that you can imagine, including like initialization, dissipation, thermalization, even quantum error correction. So, and that's actually something which we'll discuss in the next part of the talk. But just also like a quick summary of what we can do with the controls. We can prepare arbitrary quantum states, like a single photon on demand. And we can prepare unitary gates and even the most general quantum channel allowed by quantum mechanics. And just to give another higher overview about what we're doing like in these quantum control schemes, so far we've been mostly focusing on the unitary control schemes by using Hamiltonian evolution to achieve the desired unitary evolutions. Actually, you can combine the unitary and dissipations to introduce some like engineer dissipation to define some logical space, and then use a Hamiltonian perturbation, which will be projected to the logical space that allow you to implement something non-trivial, which is detailed in these references. And even more generally, it turns out that even more interestingly, just to use dissipation in itself is also sufficient to achieve like universal control. So this is actually detailed like in these references as something called holonomic quantum control. Basically, you make a closed loop in the phase space, but the evolution you get is not identity. It can give you a non-trivial unitary gates that allows you to do computation. But for the sake of time, I'm not going to the details on these different control schemes, but I will go back and continue the discussion about how to use these quantum controls and the real-time adaptive schemes for quantum error correction. So now let's talk about about the bosonic quantum error correction. So first, like I guess maybe people are more familiar with about the qubit-based quantum error correction, which basically we have like multiple qubits to get a larger Hilbert space, and with this additional redundancy or the extended Hilbert space, we are able to introduce redundancy that allows us to identify errors and to protect the encoded information. But for bosonic modes, it's actually like we do start with a very good condition that we do have a lot of energy levels. Instead of the lowest two, like a vacuum or single photon state, there are higher Fock states that we may also use for encoding information. And the additional thing is that for bosonic systems, actually the error is different from the qubits because the dominant errors are excitation loss errors or dephasing errors. And basically the photon number, if you have a single loss, if you have apply annihilation operator to a single photon to the photon state, the photon number will be reduced by 1. So basically there is, if you have dephasing error, the photon number is preserved. So basically there is a finite change of photon number associated with excitation loss or dephasing error. And this actually gives you some structure in terms of identifying errors and will lead to some specific schemes of encoding bosonic information to protect against such errors. So now, and another comparison between qubits and the bosonic system encoding is that typically for qubits, you need to have multiple qubit systems to encode one logical bit of information. But for bosonic systems, it's actually possible to consider some even more hardware efficient schemes, such as single bosonic modes. You can encode information and protect against the loss error, which has no correspondence in the qubit domain. But actually, people have been studying bosonic codes for more than 2 decades, and there are different ways to encode. You can encode information in photon number basis of a lower photon Fock states or higher photon Fock states. You can also encode information in coherent state superpositions, or like in the position momentum eigenstates or hybrid like qubit bosonic encoding. And if you look at the history of bosonic codes, then there were like quite fruitful discussions in the early 2000s. And that was when people were thinking about linear optical quantum computing. And or more recently, as the superconducting device took off, people are thinking about using bosonic modes and the superconducting nonlinearity for quantum computing. So this, now maybe one thing we want to maybe focus on for this discussion, especially for superconducting cases, actually the bosonic modes are still pretty precious. We don't want to use like just 100 modes to encode 1 qubit. So we want to mostly focusing on how to use the single bosonic modes to correct photon loss errors. And so before we actually look into the quantum encoding, it probably would be helpful to look at the classical encoding first. So in classical encoding, we also actually use single bosonic modes to encode the information. And for example, we know that if we think a coherent state, which is also used in the classical communication. So the coherent state has two quantities. One is amplitude, the other is phase. And in the presence of the lossy channel, the amplitude of the coherent state will decrease, but the phase is still preserved. So therefore, if you encode the information in the phase of a coherent state, then with some loss, as long as the coherent state do not go back to really have significant overlap with vacuum, then the phase information is still well preserved. So therefore, that leads to the encoding, which is called the phase shifted keying. So for example, you can encode the information in coherent state alpha and minus alpha. Then the sign of alpha, whether it's plus or minus alpha, that encodes one classical bits of information. And you can use multiple coherent states to encode multiple bits of information. For example, you can have 8 coherent states, and that can encode log2/8, which is 3 bits of information. And this is called the phase shifted keying, and which is actually very widely used in Wi-Fi and Bluetooth, and it's a very successful encoding scheme. So now we may want to extend such scheme to the quantum domain. So for example, a naive way to do it is just say, let's have 4 coherent states. It will span a 4-dimensional Hilbert space, which in principle can encode 2 quantum bits of information. But just recall that early on that if we want to have a capability to correct some errors, we probably want to have some redundancy that allow us to identify errors. And the scheme, if you encode 2 quantum bits of information in this 4-dimensional space, then there is no additional redundancy. And if you don't know whether or not there's a photon loss, then you actually cause a decoherence to the encoded information. So instead of being greedy to use the entire 4-dimensional space, we can actually just use the 2 out of 4-dimensional subspace to encode 1 quantum bit of information. For example, we can choose an even photon subspace, which can be constructed using symmetric superposition of alpha and minus alpha, and I alpha and minus I alpha. So you can get these 2 logical states with even photon numbers. And then by monitoring the parity, you will know whether or not there is a photon loss. More specifically, you can have these logical 0, logical 1 state with even number of photons. And you can come up with superpositions of these logical states. With 1 photon loss, it goes to odd photon space. And there is an extra phase associated with this I alpha and minus I alpha term. And if you have 2 photon loss, it go back to the even space with also extra minus sign between these 2 logical states. And if you have 3 photon loss, go to odd, and 4 photon loss go to even. And actually you find that after 4 photon loss, it goes to the same states you start with. So there is a circle of life that basically only need to track photon number loss modulo 4 for this coding scheme. And because we have the capability, we assume we have a capability to do to do photon number parity measurement, then we will be able to identify individual photon loss if we monitor the photon loss frequently enough. So that is actually what the CAD code will allow us to detect individual photon loss. And moreover, because as we shown here, that basically the coherent superposition is still preserved. So basically all the information is still preserved. And instead of adding extra photons to the photon loss, we just need to know how many photons are lost. Then we will identify how to interpret the encoded states, because that's all we need to do to preserve the information. So now the question is, how can we perform quantum non-demolishing measurement of the photon number parity? And this is actually a non-trivial, because just think conventional photon detectors, you will know the photon number, assume there's no extra imperfections, but knowing the photon number will know the parity, but it destroys the encoded state. And here we want to do a non-demolishing measurement, so that we just want to know the photon number, the 1 classical bit of information, but without destroying the photon state that encode the information. And it turns out it's possible, and here is a scheme which was developed and experimentally demonstrated in Rob Shulkoff's group. So the idea is the following. So you will use a two-level system here, which is the transmon, to measure the photon number parity of the superconducting cavity. And you start with the transmon in a symmetric superposition of ground and excited states. And you let the transmon couple dispersively with the cavity mode, with this dispersive couple Hamiltonian, as we mentioned in the first slide. And let it couple for time, which is pi over chi. And after this time evolution, you can think that each of the photon will induce a pi phase shift of the excited state of the transmon. And if there are even number of photons, the phase shift will be integer multiple of 2 pi, which induces an identity operation acting on the transmon. However, if you have an odd number of photons, then the overall phase shift will be pi for the excited states, or odd integer multiple of pi, which is pi for the excited state. So therefore, you induce a Z rotation for the GE states. So at the end, the transmon will convert it to either symmetric or anti-symmetric combination of ground and excited states. And that is something you can projectively measure and unambiguously distinguish. And that will tell you whether the photon in the cavity is even or odd. And you know that you get exactly one classical bit of information about the parity without getting any additional information from the cavity because it's still preserved after the operation. So therefore, you have a scheme to measure the parity. So now let's put all these things together to think about quantum error correction. So first we have the coding, which is CAD code, encode in the even photon subspace, and then monitor the parity, which can be achieved by having additional transmon that to couple to the cavity and read out the transmon to get the parity. And you repeat the parity measurement. And at the end, you will track how many photons has lost so that you will know how to interpret the states that are left behind in the cavity to restore the information. So this is the quantum error correction scheme that outlined here. And experimentally, here we can see some experimental data with horizontal axis as time and the vertical axis as the process fidelity. And the higher the better, and the 1 means perfect quantum memory. So in order to see like whether how good the memory is assisted by quantum error correction, we're trying to compare with the best encoding you can get without active error correction, which is using 0-1 photon encoding with a minimum number of excitations needed. And we find the lifetime is about 300 microseconds. And if we introduce the encoding, which is CAD code, but without doing active error correction, we see the lifetime is about 130 microseconds, which gets shorter because there are more photons in the cavity, so it's more vulnerable to excitation loss. However, once we put back in this parity monitoring, so that we know how to correct these errors or you reinterpret the states at the end, we find the fidelity actually goes up, and the lifetime gets longer with a lifetime about 300 microseconds, which is comparable to the best encoding you can get without doing active error correction. So this is actually what we call reaching the break even. And the one natural question will be, can we do better? Because right now it's just getting a break even, and what's limiting the performance of this active error correcting scheme? And what's limiting performance is actually when we do parity measurement using the transmon, we pay a price because during the parity extraction process, the transmon may decay because it's not as good as the cavity. So a 1 microsecond interaction time might have a 1% error during a few percent error during this parity measurement process, which causes additional cavity dephasing. Now, if you look in more detail of the diagram, so during this parity measurement, the transmon may decay at any duration within this 1 microsecond, but we have no idea when the transmon decay happened. And if decay happened and you don't know when it happened, then basically there will be some random phase shift. So you don't know how long it evolved under this excited state of the transmon, which induces a random phase shift of the cavity. And that causes the dephasing of the cavity, which causes the loss of the information. So in order to overcome that, we want to develop a scheme so that it doesn't matter when decay happened, it's okay, the evolution is as if the same as the decay happening at the end, and there is no additional decoherence to the cavity. And turns out that this can be achieved by having something called the error transparent operations. And basically, we want to achieve a scheme which is fault tolerant against the transmont decay, which is a dominant error. And the way to do it is to use a third level of a transmont, because fundamentally transmont is essentially a harmonic oscillator, which induced by the Josephson effect. So we have a third level called the F level of the transmont. And we know the transmont decay also have a structure that it only extracts one excitation at a time. So if we start with a superposition of G and F, if there is no decay, then it will evolve as if it should be, as planned, so that we will be able to read out the parity, whether in the symmetric or anti-symmetric basis of G and F. And if there is a decay, then F will decay to the first excited level called E. Then we will be able to identify the transmont decay during the process. But usually we'll just say, if we detect the error, we just discard it. But here we can do even more, because if we make the second and the first excited levels have the same dispersive coupling with the cavity, then actually it doesn't matter when decay happened, because if a decay happened at some bit of a time, because E and F have the same frequency shift, so there will be no extra dephasing to the cavity, because it will accumulate the phase as it should be, regardless whether it's F or E. So that at the end, it will deterministically undergo a unitary evolution, which means that information is still preserved. Simply, we can just undo the unitary evolution to recover the information. So this procedure, which is the crucial ingredient, is that it doesn't matter when error happened, it's happened as if it had at the end, is something which we call the error transparent procedure. And the idea is that basically the Hamiltonian and the error and the jump operator, they sort of commute in the subspace of the encoded subspace, so that basically the evolution doesn't matter when jump happened, it happened at the end, so that we can restore the information by correcting that jump error, and then the information will be preserved. So this leads actually to a more general situation, is that typically we will have like a kind of combined system, that we may have a central system, which is really good, can store information like a superconducting cavity. And we may have an ancillary system, which might not be as good, but suffer from decoherence, but it is relatively easy to control, like a two-level transmont. And we want to use the ancillary system to enhance our capability of control. But on the other hand, we don't want the ancillary system, which decoheres faster, to decohere a central system as well. So is there a possibility to kind of gain the controllability from the ancillary system, but not suffer from the decoherence from the ancillary system? And the previous example of this error transparency is one way to do it. But more generally, we think that there is a formalism called the path independence for this, like ancillary assisted control, but we don't suffer from the decoherence of ancillary. So here is kind of like a circuit diagram. You couple with ancillary and the central system, and at the end you measure the ancillary, and the goal is actually, with conditional different measurement outcomes, there is a deterministic unitary operation acting on the central system, which allows you to achieve some non-trivial quantum gates. And in order to do it, we basically want to have some like a path independent formalism. So depending on different outcome of the ancillary, we want there will be different paths that will evolve in the middle to reach this final state of the ancillary. But if the system and ancillary evolution has a certain property that regardless of which path it goes, the system will undergo a fixed unitary that only depend on the initial state and the final state of the ancillary, then actually we don't even need to care which path it goes through. We only need to know that it goes to the fixed state of the final of the ancillary. Then we know which unitary operation happened to the system, so that the information of the system will be preserved. And this path independent formalism, you can think it as a more general way to capture the special case I mentioned earlier on as the error transparent gate. And so mathematically, it corresponds to there is isomorphism between the ancillar jumps and the joint system and ancillar evolution that allows you to actually retain information in the system without suffer from the decoherence. So if you're interested, you're welcome to look into these references for detail. Yeah, but now let's maybe go to the third part, which is related to the quantum gates between the logical qubits. So here, I'll focusing on a special case that you want to, suppose you want to have like two cavities, each encode some logical information, and you want to do a gate between the two. And one way to do it is you can simply swap the information from a cavity to a transmount, and then use a transmount to couple the other cavity and later swap the information back to the cavity you started with. And this scheme, in principle, it may work, but it's actually sometimes difficult because it depends on the choice of the code. It may not be easy to swap back and forth between cavity and transmount. And also, like it becomes more vulnerable to the decoherence of the transmount during these swap back and forth operations. So one question is, actually, can we develop some encoding schemes that actually can get over this limitation so that we can perform logical operations regardless of the choice of the bosonic codes? And this may sound too good to be true, but it turns out it's possible. And the key idea is something called the exponential swap gate. And there are also a lot of things we can say about the exponential swap gate. It allows you to perform like a universal computing and the principal component analysis useful for machine learning. But the simple way of explaining it is that exponential swap gate is just a coupling between the two modes and perform a superposition of identity and swap. And because the swap square is to identity, so exponential of swap is spanned by identity and swap. And just to make sure it's clear about the exponential swap gate. So if we have a 0-1 state as input, the E-swap and the beam splitter are doing something similar. But if you have a 1 photon in each of the modes, then the beam splitter will give you this bunching effect, while exponential swap will maintain the 1-1 subspace. If you have arbitrary states coming in between the two modes, then the beam splitter will give you a very complicated outcome, but the exponential swap will just give you a combination of no swap and swap output. So in order to implement this exponential swap, actually exponential swap is very helpful because we can use it, it's preserving the code space, and we can use it for bosonic computation. And in order to implement the exponential swap, it's helpful to go through actually another gate, which is called the parity gate. It's a -1 to the photon number n. And the parity is similar to swap because parity square is identity. So exponential parity is a superposition of identity and parity. Similar to exponential swap is superposition of identity and swap. So why I go through these math is because now suppose I have a Mach-Zehnder interferometer, which is two 50-50 beam splitters, then the output will be like a psi1 times psi2. But if I shift one of the paths by pi phase shift, which is essentially do a parity operation to one of the paths, then the output will be swapped. That's what we know from the optics. And now if I can do a superposition of identity plus parity, then output will be a superposition of identity plus a swap, which is the exponential swap. And this is actually a circuit which allows you to do exponential swap by sandwiching this parity with this Mach-Zehnder interferometer. But how do we do this superposition of identity and parity or exponential parity? We can actually implement it by having additional ancilla prepared in the ground and excited state symmetric superposition. And then do a control parity operation twice, sandwiching X rotation by angle theta. So if the X rotation theta is 0, then the two control parity operation will cancel each other. Then you get just the identity operation for then you don't have a phase shift parity in the upper path. So it will give you just a no swap. And if the phase shift X, if the X rotation theta is pi, then basically only one of these control parities will be effective. So indeed, you perform a parity operation, so you get to the swap. So some intermediate angle theta, you actually get a superposition of identity and parity for the lower pass, which will give you a superposition of identity and swap in this diagram. And that is a circuit allows you to do exponential swap. And experimentally, all these ingredients are available because the control parity can be achieved by evolving under this dispersive Hamiltonian for time pi over chi. Then every photon will induce a pi phase shift if the transmon is in the excited state. So, and also the 50-50 beam splitters can be achieved by the four-way mixing so that you can induce the beam splitter by driving the two additional tones that match the difference between the two cavity modes. So therefore, you can experimentally demonstrate the control swap. And here is the data showing like a full swap operation at some logical level. And indeed, you see this nice pattern on the left experimentally obtained matches with the theory prediction. And the fidelity is about 85%. And so that is actually like something which is quite powerful that you can do the exponential swap gate that allows you to perform a quantum gate regardless of the encoding that you use for the bosonic system. And also it's universal and allows you to minimize the transmon coupling, which is only limited to the pi over chi during this control parity gates. And also it has some nice features of error detection that in case the transmon has a T1 or T5 error, then the additional output of this transmon will herald such an error if you use some additional few extra levels of the transmon. So in case people working on quantum dots, that the exponential swap is actually very similar to the exchange coupling between the spins. So if there are two levels that you are doing the swap between, then the swap operation for two-level system is actually essentially equivalent to the Heisenberg coupling between the spins. So you can say the E swap is essentially correspond to the Heisenberg evolution between spins, which correspond to the exchange gate. The difference, this similarity holds for two-level systems, but when you have more levels, then for example, that D is larger than 2, then you will have bosonic modes, will get a cavity. For example, cavity, you can do the exponential swap gate, which will be different from the spin 1/2 systems. And also for our implementation of E-swap gate, we're doing this cavity additional ancillary assisted coupling instead of the simple Hamiltonian evolution. So that's also something different. Yeah. So maybe just as a summary of this quantum computing schemes that I kind of mentioned with the bosonic system. So we can achieve like a control, universal control of bosonic modes. And we can implement the quantum non-demolishing measurement and even demonstrate some of the fault tolerance. And also we can, which for the sake of time, I didn't go to detail about teleported gates. And I mentioned about like kind of you can implement the quantum gates sort of independent of the encoding of the bosonic systems. And overall, basically you can do like the parity measurements all the way up to like a multi-qubit gates and try to include some features of fault tolerance so that you will be able to perform quantum gates insensitive to the dominant errors. Yeah. So maybe for the last few minutes, I'll maybe extend from this bosonic encoding for quantum computing to other applications such as quantum communication, quantum sensing, and quantum simulation. So for example, quantum communication, one natural extension is that maybe we can use it for quantum repeaters. Because for quantum repeater, between between different, each repeater station will perform encoding and then send the encoded block over the fiber channel, and then next repeater station will correct errors and re-encode and send to next station. And the repeater, it's difficult to directly operating like encoding, decoding in the optical domain. Maybe we can do a frequency conversion from optical to microwave domain, do error correction, and reconvert back to optical domain. And then we can consider using these bosonic codes and using superconducting circuits to do error correction. And we further look into about the potential about these bosonic codes. And it turns out that we do have like very efficient bosonic codes, such as the multi-mode GKP code. Here we can almost saturating the quantum channel capacity with just the constant offset that we still need to figure out how to overcome. But indeed, the perspective of using multi-mode bosonic code is very bright that you might be able to fully achieve the quantum channel capacity. And about using bosonic codes for sensing and simulations. And here, just to give one example, which is something called the GKP state, invented by Gottesman, Kitaev, and Preskill in the early 2000s. And this code uses kind of a simple observation. We know the commutator between position and momentum is equal to a constant I. So, which means that if we consider a displacement along the position and along the momentum, and if we want to change the order of these two displacements, there will be an extra phase associated with it. And this formula you can derive from the BCH formula. And then that corresponds to, if you move these two terms to the other side, it corresponds to if you move a closed loop in the phase space, there will be a geometric phase associated, which is proportional to the area of enclosed in this closed path. And if this area is proportional to integer multiple of 2 pi, then this operation is equal to 1, which means this coefficient is equal to 1, which means these two operations commute with each other. So we can, for people familiar with error correcting code, you can come up with stabilizers because these operators commute with each other, and use stabilizers to define a logical code space, to define like a code or code space. And here there's only one particular code, which is state, which is destabilized. So that's called the GKP state. And the GKP here is a Wigner function of a GKP state. You see the periodic structure, and also very focused points on these Wigner functions. And here is the GKP states with the marginal probability distribution associated with the position and momentum. You see very narrowly distributed position momentum spikes, which indicates that if there's small displacement in position momentum, you will be able to shift the states. And moreover, because these stabilizers, they commute with each other, which means in principle, we can simultaneously measure the quantities associated with these quantities with the stabilizers, so that we'll be able to simultaneously measure the shift in position momentum modulo square root of 2 pi. And that actually is a bit you can think it as a way to evade Heisenberg condition, Heisenberg uncertainty principle. But here, the difference is that here we're not measuring the full shift of position momentum. We only measure shift of position momentum modulo square root 2 pi. So this actually enables us to measure small shifts in position momentum if we use a GKP encoding as a sensing tool, or we can use it as an ancilla to measure the shift in position and momentum. And that actually enables us to even perform some schemes, which here, maybe for the sake of time, I just show the the punchline. We can use the GKP combined with some bosonic code, a bosonic state, unknown bosonic state. And at the end, we can use this error correction scheme to suppress the photon loss associated with the added noise of the bosonic modes, and then suppress the noise to the quadratic order. So that sort of allows us to do an encoded bosonic system while preserving the bosonic nature at the logical level, so that we can maybe even consider do a boson sampling at the logical level, or simulating bosonic systems, or bosonic sensors using this logical encoding. So maybe for the sake of time, I think that's maybe what I want to talk about on these, how to use the bosonic systems for various quantum information tasks, and go beyond the limit of the excitation loss, the coherence time limited by the bosonic system itself. And in the end, I'd like to thank the group members and also the collaborators on both theory and experimental side. Thank you for your attention.
Thank you, Liang. Thank you. That was it's very rare to have a talk that has so much meat and is also very clear. So thank you for that. So we have some questions. So there's a question from Mark Wild. Mark, do you want to unmute yourself, or maybe I can unmute you if you can't? Okay, you have been unmuted.
Oh, thanks for that. Thanks for the talk, Liang. So my question was, you started talking about quantum capacity, and I'm wondering if you have M bosonic modes, is it experimentally possible now to create arbitrary superpositions of photon number states. And the reason I'm asking about that is if you study Devitak's proof of the quantum capacity theorem, you realize that such states achieve the quantum capacity of the pure loss bosonic channel.
That's interesting. Yes, I think that's a good point. Yeah, I would say in principle, like for single mode, one could achieve like arbitrary superposition of different photon states. Assume, okay, there's a cutoff, okay, because otherwise it's not bounded. It's hard to
we were just
make a rigorous claim. Yeah, and I think okay, we in principle we can also extend this universal control to multiple modes, and to create like an arbitrary superposition of photon states for multiple modes. And so maybe one question would be like how many modes you need kind of in order to kind of approaching these capacity. And the other is that suppose the codes exist, is there like some like efficient like error correction schemes that one can maybe like relatively easy to implement to achieve this like quantum channel capacity. So may I know if there's some structures for those codes that can achieve the capacity?
Yeah, so typically to achieve capacity, you need a lot. There is an explicit scheme called polar codes, and it might be interesting to study the performance of polar codes in the bosonic context. There was a previous paper of Joe Rennes and others about this, but they didn't consider these particular states that I'm mentioning. So.
Yeah, I think that's actually an interesting thing to look into. Yeah.
Okay,
thanks.
Thank you.
Thanks. Any questions? So if you have questions, you can put them into the chat box. And so while people are thinking, I had a question about the error transparent gates. Is there any notion of error transparency or path independence that takes into account sort of measurement errors?
Good question. And that's something which we hope we'll be able to extend in future investigation. And right now, the dominant error, as shown like here, is actually like the error that during the like parity acquisition. And also like you talk about the measurement error, and there was actually a recent work we had with Rob Shukov's group, is that if you have a capability of doing like repeated readouts, QND readout of the states, for example, you want to measure a state which is stored in the cavity, and you want to use a transmon to repeated readout, and you can achieve a fidelity which has 99.99%. And even for a transmon, if you push the excited state to the F level, and you can repeat the readout, that could allow you to read out longer, and that will also boost the fidelity. So essentially, I think that the readout fidelity of this ancilla can be significantly boosted, and we think like 99% or even higher should be like should be codes quite generally for many superconducting platforms. Yeah, but that's a good question. Like it will be nicer if this will be also like immune to the readout error. Yeah.
Okay, but I guess you're saying that readout error will go down more quickly, so it's not currently what you're worried about, or
And yes, and also like for this experiment, which I think that the readout error is indeed like pretty small, which in this paper it's actually not the dominant error. Yeah.
Okay. Looks like Mark has another question, so I'm gonna unmute you, Mark.
Thanks. Yeah, can you go back to the slide where you were talking about the sequential implementation of quantum channels? It was a bit early.
Yes.
So you have a lot of unused slides. It's very interesting. Yeah, to me, this was very new. I hadn't actually seen this before. I thought this was very interesting, and so I'm interested in looking at your paper on the left, diving in a bit more details. So just to understand, in your paper, do you describe this in a purely theoretical, with purely like quantum information language, and then do you go on to discuss how this is implemented in the cavity modes, et cetera?
Yeah, so in the paper, we're actually like thinking about start with the D-level system. And then like you can, actually, this is a slide which might be of interest, is that we have the explicit construction of the unitaries. Or more generally, it's kind of isometry that you want to implement in the middle. And so suppose you know your CPTP map, you know the list of cross operators. You can put it at the end. And this is kind of a binary tree. This kind of determines that suppose you go kind of backwards. You get to know what the unitaries you need to implement at the later stage. And then combine these, you can get what unitary you need to do like at the round 1, and then put back what unitary to put in round 0. So this binary decision tree will tell you what unitary to apply. And everything can be computed analytically.
Okay.
Yeah. So,
yeah. So to compute these operators, there's an efficient algorithm also?
Yes, it's basically matrix multiplication, and you need some like a pseudo inverse in case that certain things gets 0. But other than that, I think everything is determined. And also the answer is not unique. It depends on how you arrange the cross operators. You'll get a completely different solution. Yeah. Yeah, but I guess one thing which we still, I think it may be an interesting question, maybe invite people to think about, is that how to make this fault tolerant, right? And maybe there are better designs. There are multiple solutions. Maybe one solution is more better than the other because it's less sensitive to errors. And is it possible to introduce redundancy so that if there's something wrong here, but it will not affect the later circuits, that will be much better. Yeah.
And then just to follow on with a quick other question, this scheme works if the input dimension is different from the output dimension. Does it work in the more general case also?
Yes, I think it should work. Yeah.
All right. Thank you.
Okay. So there's a question from Jiayu Wang. He's asking, so how is the scaling of the bosonic error correction? So above break-even point, a single mode bosonic code might still not be good enough for running real algorithm. What would you expect as another level of error correction on top of the single mode code?
Yeah,
Maybe.
I think that's that's the end of question, right? Just make sure I'm not missing part of it. Yeah, maybe repetition code or Tori code. Yeah. So I think that's and this is something which I think is still pretty open. And one easy way is say, okay, we just do the bosonic coding, and then you cannot concatenate because the logical encoding in this case is a D-level system, and you can use what we know about the qubit coding and so on at the higher level, including the surface code, if you prefer. And actually, maybe recently there's some results from like both in collaboration with people at Yale, like Shruti Puri, especially, and also like from another group in France, Mazia Mirahimi. We will look into like this something called the bias preserving operations. So if you look at the CAT code, it actually has a nice structure, like these different coherent components. They're well separated, so that it's unlikely to make error that go from this state to that state. So therefore, that basically there is no like X rotation in this case, but there's maybe some dephasing associated with this. So in that case, then the error is kind of biased, and you can come up with a full set of gates that preserve the bias of the error, so that you can imagine that once you do the bosonic code, the next level, basically the error is probably dominantly like say the dephasing error. And then you can just use the repetition code to correct the dephasing error, which is much, much easier and much more resource efficient compared to the generic code that correct both bit flip and dephasing errors. And there was actually a recent paper appeared in Nature Physics that by Zaki Lisa which they demonstrate that indeed the cat code can give you an exponential suppression against one type of error, while the other type of error only grows linearly with the size of the cat. So I think that's actually a very nice experimental demonstration showing that indeed that there's a possibility to preserve the bias, to further to make the code which is really good against a certain type of error, so that maybe at the higher level, we only need to focus on one type of error instead of both bit flip and phase errors.
Okay. So basically, in your view, the way forward is these biased qubits or bias preserving qubits, gates and stuff.
Yeah, I think that's one way to do it. I'm sure there are maybe other ways to do it. It's just like one way which I'm aware of. Yeah.
Okay. So I'm looking at the chat box, and it doesn't look like there's any more questions. So I'm gonna stop the recording, and maybe we can give another round of applause for virtual applause for Liang for such a nice talk. So
Okay. Thank you. Yeah.
Thank you. Okay, so I'm gonna stop the recording.